The date is April 12th, 2024. My name is Hanson Su, and I'm here with Professor Emeritus Jeffrey Ullman. And so let's start with where and when you were born.
Well, I was born in Boulevard Hospital in Queens, New York. It was November 22nd, 1942.
Okay, so where did you grow up?
Well, let's see. Basically in New York City. We moved, after World War II, we moved out on Long Island. And I went to Van Buren High School in sort of eastern Queens.
Okay, so still in New York City, not
it was in New York City. Yes.
Okay. And what were your parents' backgrounds and occupations?
Okay. Well, my father went to college. Actually, was an English major. Discovered you can't actually get a job as an English major. Wound up in advertising. Basically worked all his life doing advertising. One matter, one company or another. My mother, of course, was born during the Depression, as they both were, and she went to basically what you might call secretarial school. Worked as a secretary until she got married, and then was a stay-at-home mom.
Okay. And do you have any siblings?
I have one brother, Alan.
Did your family have any strong religious political beliefs?
Actually, my father was sort of anti-religion. He grew up in an Orthodox Jewish background, and sort of felt that was rather constraining. We eventually, when we moved out to Long Island, joined a Reform Jewish temple. We've always been, the family has always been, Democrats politically. My father, told me never to cross a picket line. For example, this was a big deal in those days.
So your father, growing up in the Depression, I guess, much more sympathetic to the working class.
Yes. Well, I wouldn't say much more. I think we're still sympathetic.
What were your favorite subjects in school?
I was obviously a math guy. If we're still talking about high school, I took all the math, the sciences. Did, of course, less well in the humanities kinds of things. You probably get that a lot at the Computer Museum.
But your father was an English major, so did you get that from your mother's side?
No, that's interesting. The mathematics actually does seem to run in my father's family. I have some cousins. One was a professor of mathematics at University of Michigan. My uncle, my father's brother, was a CPA, and so on. Another cousin actually married Herman Chernoff, one of the leading statisticians of our era.
Right. Okay. Wow. What kinds of books did you read or media did you consume?
Well, let's see. It's trying to think. I used to do my homework. Again, I'm thinking about high school period. I used to do my homework listening to the radio tuned to a rock and roll station. That was a new thing at that time. Late 50s. Books. I know. I read some interesting science books. But it was not a big thing with me. I don't know. I just I'm trying to I'm trying to think what I read for recreation, and it was I don't know. I think sort of keeping up with schoolwork. They required you to read in high school to read certain of the well-known novels. But it was not a big thing, I guess.
Yeah. Okay. So, what were your hobbies then?
Oh, hobbies. Well, again, thinking in the high school era, I got into a group of guys who played bridge. We were actually. I should give a shout out to. We had a high school math teacher, Ira Ewan, who passed away recently. And he took, he found a group of students, high school students, and he sort of took us under his wing in the sense that he would drive us around after school and just sort of lecture us on stuff, on interesting mathematics or his experiences. He had gone to Harvard, his experiences in Cambridge, where apparently they had, for example, restaurants that hadn't reached New York. I remember him telling us the wonders of eating kimchi, for example. But basically talked about mathematics and encouraged us to learn to play bridge. He was a life master at that time, which was a big deal, much more of a big deal than it is nowadays. So we had a foursome played bridge. Was in the Scouts for a while, and it was actually the same guys. We'd go off on these retreats in the woods and basically spend their time playing bridge. It was, I played. I played piano. That was still play by ear. Sort of forgotten how to read notes, but I guess I'd call that the closest thing I have to a hobby these days.
Did you have any influential teachers or mentors or role models?
Well, as I said, this fellow Ira Ewan was really the person who, let's say, solidified my interest in mathematics. Later on, again, I don't know if you want to progress to to college days.
Well, we're getting there.
No,
we're getting there soon.
Okay, so I'll leave. In high school, I think this fellow Ewan was the guy.
Okay. Who were your heroes growing up?
Hard to answer. I didn't. Yeah, that didn't seem to be a dimension of my life at that point.
Okay, so let's move on to college. So you started college where and when?
Okay, well, in '59, 59, I went to Columbia. It was.
And how did you come to choose Columbia?
Well, they gave me a scholarship. See, my father, especially at that time, he had I think some let's say financial reversal. He started his own. Remember, he was in advertising. He started his own firm, and he got, if I recollect, his major client basically went bankrupt, didn't pay him. So he was not in good shape. So I really had to go where I could get a scholarship. And in those days, it wasn't need-based. So you had they gave it to people with good grades regardless of their financial status. So I got a scholarship from Columbia, which, by the way, was just prior to the class of '63, starting in '59. I was in the first engineering school undergraduate class. Prior to that, Columbia had only had graduate engineering. And I think they really wanted to populate the class, so they gave me a scholarship, and that was that sort of decided it.
Yeah. Where else were you also looking at?
Well, I got into MIT, but they wouldn't give me money, and I think I applied to RPI. I think that, and then the city colleges also. I think that was pretty much it.
Yeah, and so you said you started. You were in engineering. Your major was?
Well, it was what they called engineering mathematics. So I was able to take the core mathematics classes that the mathematics majors in the college took, and then, in addition, we're supposed to take a year of an engineering subject. So I started off in civil engineering, and that turned out, I don't know, kind of boring. So I switched to electrical engineering in my senior year, and took the basic courses. Like for example, we learned how to build circuits with vacuum tubes. Give you an idea. Let's see. Well, okay, because that's
so
answers your question.
So your official major was engineering mathematics, but you also could specialize.
Well, they had to. That was how the engineering mathematics works. You took the core undergraduate mathematics subjects and a year of engineering.
Oh, okay. So the major that you graduated with is still engineering mathematics and not electrical engineering.
That's correct.
Okay.
But then I went to graduate school. I went electrical engineering.
Okay. And So how did you decide on engineering mathematics in particular?
Well, again, I really wanted to do mathematics. I went there having, no idea.
It was because of the scholarship.
No idea. It's all right. Funny story. I'm going to go back to high school again. I had this friend, Ronnie Walters, who was one of the bridge players. And one Friday afternoon, we decided we were going to raid the chemistry lab and steal some jars of chemicals. And so we walk in there, and the chair of the science department is sitting there. Okay, so plan was aborted, and he's opening his mail from the week, and he says, and he finds a letter from Columbia University School of Engineering saying that they are offering each high school in New York City the opportunity to send 2 students to a Saturday enrichment program. And of course, it's Friday afternoon, everybody's gone. And it was the next day. And so he says, okay, you two, you're it. So we go to this enrichment program, and it was interesting. I remember receiving, for example, a lecture on Hamming codes. This was, as part, and remember, the whole purpose of this was to drum up business for the undergraduate engineering school. So they had a counselor who would give us advice on which colleges to go to. And, so he sits me down and says, well, I've heard MIT is good and so on. But then there's also Columbia Engineering, and we're going to start this magnificent program, and you really ought to apply to that. So that's how I even heard about, Columbia Engineering as an option. Otherwise, I doubt, for example, that my high school counselor would have been aware of this. But the whole point is, I didn't really understand what engineering was, right? I mean, it's, looked to me, like mathematics of, linear algebra with Hamming codes and stuff like that. That's what it, I had no idea what the difference between science and engineering was. They don't teach you that in high school, or didn't at least. So when I, sort of realized what it was about, and a lot of the courses I took were just standard courses, and the physics and the calculus and the, and then I started, on things the engineering basics, like mechanics, thermodynamics, which were sort of a little less interesting to me, I guess. So it seemed to make sense that the best I could do in this circumstance was to go engineering mathematics. Turns out, however, that I guess engineering really did suit me. It is the kind of, I really am at core, it turns out, an engineer once I found out what it was really about.
Rather than a mathematician.
Yeah, pretty much. That is, I care more about, what's it worth than, how does it show I'm smart, or whatever it is mathematicians actually do.
Okay, let's go back to the question and we postponed. So who were the important influencers at your time in college?
Yeah. Okay. Well, let's see. Again, the I wouldn't say it so much influences. I mean, there were some professors that I liked better than others. Omar Wing taught us the electronic circuits course. He's a cool guy. Jacob Melman, again, who taught us vacuum tube electronics. But I guess the way I really got started was, okay. In my junior year, I found out about a field known as actuarial science. It's basically mathematics applied to the insurance industry, life insurance in particular. And the thing about that was I discovered I could advance in the field by taking exams. And I was kind of good at taking exams. And so I took the first 3 out of the 8 actuarial exams, and I did very well. The first 2 were really just like SAT exams. And then the third was discrete mathematics, which I sort of taught myself. And armed with that, I was able to get a job at an insurance company.
While you were still in school?
Well, for summer job after my junior year. And, they saw me as a big prospect as becoming an actuary. So what did they give me to do? They had this, they apparently had an IBM 650 computer, which they didn't let me touch. But there was another machine, I think it was a Burroughs 200 or something like that. And it was sort of like the size of a refrigerator on its side, which you programmed by sticking pins into boards. So if you wanted to, for example, add location 25 to the accumulator, you would put a pin in an A, a pin in a 2, and a pin in a 5 in 3 different fields. And that was basically how you programmed the thing. And then you'd take the board and you'd plug it in to the top of the machine. And so I learned how to use this machine. I was sort of the assistant to the guy who was responsible for it. And he went on vacation, and for 3 weeks or something, I was in charge of the computer. And I wrote code. It was a very limited machine. I think it had like 100 memory locations, and beyond that, you had to put instructions using paper tape, and so I rewrote their code to compute premiums in some situation. I forget exactly what it was doing, but what I tried to condense the program by simply not doing rounding at every step, but simply rounding at the end. And after I got it done, I showed him, hey, now you can run this thing without paper tape, because it all fit on these boards. I think it had like 120 instructions was the max you could do. And they said, yeah, but we can't duplicate the computer's calculations, so your code's no good. Because we'd have to have human beings carrying out to, I don't know, 6 or 8 decimal places all of this calculation. And we don't do that. We always round everything to the nearest penny, which they should, I guess. But all right, so I learned my lesson there. Then after my senior year, I got a job out of Brookhaven National Laboratories, and they had just gotten an IBM 7090, and so they sent us all the summer interns a FAP manual. FAP was Fortran Assembly Program. It was the assembly language that was available on the 7090. And of course, I didn't understand what to do with it. So I basically memorized the instruction codes. So, I remember, for example, integer add was octal 0500 on the 7090. So I still know that.
So you became a human assembler.
Yeah. Yeah. I guess you could say that. And then when we actually got out to Brookhaven in the summer, they sort of explained to us what you actually do with this stuff. And so I spent the whole summer writing a program to recognize electrons in bubble chamber photographs. Interesting program, actually. But the guy, my boss there was a guy by the name of Sidney Heller, and he was really an electrical engineer. He was designing the devices that would record these pictures, and he discovered there was a little company up in Maynard, Massachusetts called Digital Equipment that would sell him a board that had 3 gates on it or something, and he was just so amazed at being able to build with this sort of equipment. But at any rate, he taught me a bit about digital logic, and as well as supervising my program. I think it was still. I don't know if they ever used it. It was actually kind of clever. The problem was basically I'm looking for circles in a black and white pixelated. They didn't even have these terms, but it was basically black and white pixels. And what I did was basically I took random sets of 3 points, try to find the center of the circle that contained them, and looked for common, or looked for a lot of centers similar to in a similar location, and that would be a clue that there might be a circle at that center in that radius, and then I could check to see if in fact the circle was complete. Anyway, so end of story.
Okay, great. So those were your first experiences with computers and with programming.
That is correct.
Okay. And then so this Sidney Heller was one of your important mentors.
Yeah. Well, I think he had a great deal of influence on my life.
So you graduated in
63.
63, okay. And so then you had to decide whether to go on to graduate school or work?
Yeah. And work didn't look all that appetizing. You know, again, I decided to go for a doctorate because it protected me from having to go out and work. And I had a good friend at that time, Ricky Galen, who did go to work, and he told me, he's spending his days filling out orders for nuts and bolts, and I didn't really want that, but I had no real plan to, let's say, go into academia or research. I had no idea what that was, really. It's funny how well informed young people are these days about career tracks and everything. I just stumbled from thing to thing, without any sort of target, or idea of where I wanted to wind up.
But did you know you wanted to continue in electrical engineering?
Well, yeah, it seemed to be. I liked it a lot better than the civil engineering that I had taken earlier. Seemed to be more interesting.
And after your experiences with the summer internships, did you know you wanted to do something with computers as well?
Well, again, I don't think I thought really deeply about it, but here's what happened. Well, again, funny story. First of all, the idea of going across the country. Remember, I lived in New York City. The idea of going across the country didn't make sense to me. It wasn't something that people did. Around 4 years later, my brother did go to graduate school at Stanford, but for me, I just applied to local schools. So I applied to Princeton, Cornell, Columbia, of course. Maybe a couple of Brooklyn Tech was a thing. I think it's now part of NYU, but it was actually pretty decent EE department in those days. I also applied for an NSF fellowship, which I got. It was very easy to get them in those days. They were giving a lot of, relative to the number of kids who were going on in science and engineering, they were giving a lot of fellowships. And I got a nice fellowship offer from Princeton. I think it was like $2,000 a year, to give you an idea of the scale, whereas the NSF fellowship was only $1,800. Okay, and so I took their fellowship, and I told NSF that I was not going to accept theirs, and then I got a call from the chair of EE at Princeton saying, you really ought to take the NSF fellowship instead, because our fellowship, while it's a little more money, it's only for 1 year, and we're not promising you anything, whereas the NSF fellowship would be 3 years. And so you really ought to take that. I said, yeah, I would, but, it makes sense, but I just turned it down. And he says, well, that's all right. I'll take care of that for you, which he did. and so I had the fellowship for 3 years, which, by the way, was all it took to get a PhD in those days. Again, things were very different. For example, I had not published a paper before I graduated. Today, we at Stanford, we have had applications for beginning assistant professors where they have 100 publications already. It's just very different. So I don't know. We're on to graduate school.
Yeah,
now?
we're on graduate school.
Yeah.
Yeah.
Okay.
Yeah.
I had again, just sort of backtracking. In my senior year in college, I had taken a course in coding theory taught by a fellow named Bob Chen, who at that time worked at IBM Yorktown. And I found that very, very interesting. Again, it was mathematics applied to a real problem. And so I got a job. Let's see. The summer after my first year in graduate school, I got a job working for him up at Yorktown Heights, and he basically started me off on a thesis, what became my thesis topic, which was synchronization error correction. Normally what you do is the assumption is that the bits the bits are where they are. They might flip. A 0 might become a 1, or a 1 might become a 0. Sometimes in some models, for example, if you're barcode scanners, will sometimes they'll actually just miss a bit, or in the case of like a barcode, it could read one wide line as two narrow lines, so it looks like effectively an insertion of a bit. So I was trying to correct insertion and deletion errors, and this eventually became my thesis. I guess another person who was very important in my life, my second summer, I got a job working for Seymour Ginsburg, and then I finally made it to California. He was in Santa Monica. It was a spin-off of Rand Corporation at that time. And he was working in automata theory. And of course, what Seymour did was he basically beat rigor into me. He was he was basically a theorem prover, and he even having gone through undergraduate mathematics, I didn't really understand the difference between a proof and let's say a plausibility argument, so he I think, forced me to think more rigorously than I really wanted to. And frankly, I think he sort of went a bit overboard. Especially in the sense that he was more interested in, in proving cool results than asking, what do you really need? On the other hand, it did really. It basically turned me into a theoretical computer scientist, which is it's obviously the way I have worked all my career. And so then when I got back to Princeton from my third year, there was a new faculty member, John Hopcroft, and he had spent the summer working on automata theory, and in fact, had proved something which Ginsburg had also proved, and I was unfortunately able to tell him that this was that it had just been done, anyway, we certainly Hopcroft, and I certainly recognize that automata, especially finite automata theory, context-free language, and so on, were interesting subjects and useful subjects at the same time, let's see. I guess. Well, again, I graduated at the end of my third year and went to work at Bell Labs. John, then I think the year after that, he took a sabbatical at Bell Labs, and so we started working together there.
So was John your thesis advisor?
No, he was not.
Oh.
I actually had two. I had Art Bernstein, who was a coding theorist, but Art left after my second year, spent his career at Stony Brook. And so Archie McKellar, who was also a coding theorist that they had just hired, sort of took over. But really, it was Bob Chen was really the guy who effectively, supervised me.
Even though he wasn't on the actual...
He wasn't on the faculty, but he was the one who basically told me, he gave me the problem and vetted what I offered.
Right. There's a sort of a repeated theme that I'm hearing that you've been. It seems like you've been much more influenced by your summer jobs and summer internships than what you actually learned in school.
I guess that is the truth. And again, is it just me? I don't think so. But again, we remember this was many, many years ago, and the world was quite different. What I guess is that academics hadn't yet really adjusted to the idea that, at least in a field like computer science or electrical engineering, you can do research work that actually, has a value beyond writing a paper or a book. In industry, of course, they understood that, and so that's probably. I think that's why. Yeah, my summer jobs were the things that really directed my career, because they were doing the things that kind of made sense to me.
Talk about meeting Al Aho.
Well, he says we met on the registration line at Princeton. Because we were classmates in graduate school, started at the same time. He says we met on the registration line. Could be. I don't remember that, but there were 5 of us. Okay. I'm sorry. I got a point that was missing, and another one of these little things, where a tiny decision has a big outcome. When I registered for Princeton graduate school the first time, I had to check one of 3 boxes. They had 3 graduate in electrical engineering. There were 3 research programs. There was solid state electronics, communication systems, and digital systems. These are run by the 3 professors who are actually running graduate programs at the time. Ed McCluskey was doing digital systems. John Thomas was doing communication systems. And by the way, he had, for example, Bob Kahn was actually a student of John Thomas. And then there was the solid state program. George Warfield ran that. So I had to check a box. Well, remember, I had been working for this guy who was buying stuff from Digital Equipment Corporation. So I said, I'll check digital systems. Okay. And that basically made me a computer scientist, although I didn't know it at the time. And again, there were 5 of us, including Al Aho, who had checked that box. Okay, and so we were a cohort, so we basically hung out together. It was really the 5 of us. Al joined. We really only started working together when at Bell Labs, which both of us had joined initially, because Al pretty much stayed there his whole life.
And let me see here. We already discussed your internship at the Systems Development Corporation. That was what you had already talked about.
With Seymour Ginsburg.
Yeah, with Ginsburg, right. So we got that. So that was also what led to your interest in programming languages?
Well, yeah, if you can call it that. It was really, parsing was the right. I mean, Ginsburg was also. He was writing his book about context-free languages, and that was his actual interest at the time was context-free languages rather than finite automata, which he had been doing previous couple of years.
And like Chomsky's work had already been out by this point.
Well, yeah, Chomsky's paper was 56, right, I think. But remember, I mean, John Backus was using the same notation, the context-free notation, and it was, the context-free grammar idea. It was known in certain circles, let's say, as an interesting concept. There was, I think, one of the key things that is the Bar Hillel, Parlis, and Shamir paper on the pumping limit, how to prove that something doesn't have a context-free grammar. Very, very interesting idea. That loomed very large.
Okay, so you graduated and joined Bell Labs in
66.
66, yes. And then which group did you join?
Well, it was Doug McIlroy's group. It was, again, one of the an interesting story which people today may not even realize was Bell Labs was a unique situation in the sense that by law AT&T was required to put 1% of its revenues, not profits, but revenues, into research. And so basically, Bell Labs, you could get money to do anything. So they'd hire you and they'd tell you, well, what they would do is basically they'd hire anybody, with a PhD and tell them, okay, you figure out what to do, and so with, I guess I was able to do that with the help of Aho and John Hopcroft when he was there, and then, some people liked that. I liked that. Other people kind of got lost and didn't do anything. And in that case, they would just say, okay, well, here, we're going to make you a supervisor in one of the development divisions. So they'd get really good people into their development, as well as a decent number of people who were just setting their own agendas, didn't have to file for research grants or anything, just did whatever they want. And this McIlroy's group was one of these things. Unix basically came out of there. I didn't do anything of that magnitude. Again, we were, but Al and I were both in that group. And we got interested in parsing, more, not really programming languages per se, but and I guess in addition to writing the books on compiling, we did come up with a scheme which became YACC, which was Steve Johnson. Steve Johnson was the one who said, "Hey, we can actually build this." To us, it was just a paper to write. But he said, we can actually put this into practice, and it, I guess it's pretty much deprecated at this point, but for decades, people would use it. That was the way you wrote a parser.
Yeah. So the work that you focused on initially was formal language theory and automata.
Yeah. Right. Yeah, and a lot of it, a lot of it was really dead end stuff. There was a sense, okay, finite automata are really interesting. You use them in lexical analyzers, and they model simple protocols of all sorts, and context-free grammars. Languages are obviously important in parsing. So let's look at let's try to invent other kinds of automata and see what they can do. And that turned out to actually be a misguided approach. I didn't realize it at the time. But the thing is, you don't, what we were really looking at was structure of organization of a program. So, for example, we looked at stack automata, which was an idea that Seymour Ginsburg had, where the normal parser is a push-down automaton in the sense that you have a stack, that you just operate, inserting and deleting at the top of the stack. So I said, what if you're allowed to send ahead to look at a read-only way to look at the stack? Okay, well, Hopcroft and I, we proved some very, very complicated, or at least at the time complicated, facts about what kind of languages you could recognize in using that architecture. But the thing is, you don't pay for organization. You pay for time, you pay for space. Okay, and that's why all of the questions about can this kind of automaton recognize this language or do this, implement this, solve this problem, turn out to be irrelevant. The only questions that are really interesting are how much time and how much space does it take to solve a problem. Okay, that's one of the great lessons I think that I learned about what not to do. But at that time it was what did we know at the time, right? We it seemed like interesting questions, so we asked them and tried to answer them.
What was the culture of Bell Labs like in those days?
Well, again, in the group that we were in, you basically you did, it was a real research culture in the sense that each individual could set their own directions. And the job of management was to help them, to provide the resources that were necessary. That's, for example, how Unix got going. Was Sam Morgan, who was then the head of the center of which Doug McIlroy reported to Morgan. They needed a PDP-11 to develop Unix, and he found the money, give it to them. But it was it was Ritchie and Thompson's. They said, we want this, that's what we want to do, and then they did it.
So describe your working relationships with John Hopcroft and with Aho.
Well, I think we had, great. It was great. we worked on. I mean, the three of us worked on this book on algorithms, which was overly mathematical, but did sort of, it became a staple for a computer science instruction at that time. Well, let's see. I mean, Hopcroft and I, I remember when John came up to Bell Labs on sabbatical, he said, hey, Ullman, you want to be a famous person, you got to write a book. And, he was, he is my senior. I said, okay, well, if you say so, all right, what are you going to write a book about? And I said, he said, well, what do we know? Well, we know automata theory, so let's write a book about automata theory. And we did that. And we really stumbled around. Had no idea how to write a book. Moreover, I mean, it's so incredibly easy to write books these days. But in those days, how did we write a book? I'd go home in the evening and I would scribble. Maybe 20 yellow sheets of text, and then we would give it to poor Jerry Markey, who was the department secretary, to type up, and then that would be part of the book. And then, of course, it would be no good. We'd have to correct it, and so she would put these white strips over part of it and type over the white strips to correct things, and somehow or other, we managed to put a book together, with again, poor Jerry Markey's help, and then you gave the basically typed up manuscript to the publisher. They typeset it. You could make corrections. You had a budget of corrections, which we way exceeded, and they were going to take them out of our royalties, but the book sold enough that they decided to waive that. But I mean, it was just even in what they call page proofs, where you're really not supposed to change anything bigger than a comma, because otherwise you have to move things from one page to another if you do an insertion. And we were still rewriting the thing. It was amazing what a hack job that was. But we learned. And then by the time we did the second book, I think we were a little bit less error prone, put it that way. But I don't know, and it was just really a lot of fun working with these two guys, or in some cases with just with one of them. They're both just very easy to get along with, and I was very, very smart. I have to admit that, especially in the work, the research that I did with John, that he did the really hard parts. It wasn't the harder results were his, the easy ones were mine, I guess.
So the first book on automata was 1969.
Yeah, I think. Yeah.
And then the second book on algorithms was 1974.
Right.
So how important was that algorithms book in terms of devising new algorithms and classifying existing algorithms?
Well, let's see. Of course, I don't know. It's hard for me to tell whether people picked up that book and then used it to develop new things. I think one of the things which I think was good about the book was we did try to isolate algorithmic methods, things like divide and conquer, which people had talked about. Things. Al Borden, who coined the term and then used it in a paper of his. I assume that the method, the chapter that we wrote about different methods of techniques of building algorithms was more important than the actual algorithms we talked about. Although I assume many people studying computer science in the 1970s probably did learn basic ideas like hashing and so on from the book.
So why was it important at the time to develop algorithms for languages without the go-to statement?
Well, again, when you talk about algorithms, I assume you're talking about things like code optimization, right? The interesting thing about is, let's see, there's this this notion of a reducible flow graph that I think was due to Fran Allen and John Koch. And the interesting thing is when you don't have a go-to statement or anything equivalent to it in your programming language, you're basically forced to write flow graphs that are reducible. And there's probably not, you can read about it if you want the definitions, but just to say, a lot of algorithms involving code optimization are easier if you can assume that the flow graph is reducible. They're more efficient, and so that Dijkstra's original idea of go-to-less programming, it was there. His goal was not to make compilers more efficient, but to make programs more easily provable, because he believed that you could actually prove programs, something which we've never really done to any extent, but also understandable. Okay. That if there was this reducible structure to your program, you could understand, you understand the little components and then you see how those fit together into higher level structures and so on. So the programs became more understandable if you were forced to create reducible flow graphs. I think that's what it amounts to.
So it was kind of a nice side effect, I guess, or even though that wasn't Dijkstra's original idea.
Yeah. I would. I never really thought about whether the ideas are connected, but yeah, a nice side effect is probably a good term.
Okay, so then so there was also a book that you wrote with Aho on language theory.
No.
Let's see, theory of parsing translation.
Yeah, right. That was our first attempt to do a compiler book, but it was more the theory than the pragmatics, and then we did the Dragon book, was we sort of got our head together and we sort of realized what is important to tell people about compilers.
Right. So between that first book and the Dragon book that was when you worked with Aho and Steve Johnson on YACC.
I think that's right. Yeah.
Oh, okay. So we talked a little bit about YACC before. Is there anything you want to add about that?
No, I think we covered it, if I recollect. Yes.
Yeah. And so you mentioned that Steve Johnson was the one who implemented the ideas.
Yeah, right. He wrote YACC.
Mm-hmm. So how did that collaboration begin?
Well, let's see. At that time, because I was teaching at Princeton, so I wasn't quite on the scene that much. But I think that he just sort of saw the paper that. I guess Aho and I must have written a paper which would initially be circulated as a Bell Labs internal memo, and he saw it and he said, hey, this could work. Basically, and he decided that he would spend his time actually writing the code, and producing it as a Unix command.
Right. Okay. So how did the Dragon book come about?
Well, again, Aho and I, we did the theory of parsing, and it sold reasonably, but we kind of decided we'd gone overboard with the theory, and there were more things to tell, like YACC and some of the stuff that we've been doing in code optimization, or I'd been doing with some of my students down at Princeton at that time. That there was that they were just interesting, things that involved some theory, but really could get used directly, and were being used. So we decided we needed to write another book, and with a same topic but different orientation, which we did.
Mm-hmm. And talk about the reason for the dragon on the cover.
Yes. Bill Greiner, who was the editor at Addison Wesley, he said, do you guys have any idea for a cover? And I have to admit, I guess I was a little bit cynical about the real value of what we were writing. Okay, and so I said, well, why don't we? I sketched it out. The knight fighting the dragon using the weapons that we were talking about in the book, like LR parsing and I think I forget what the labels are. But, and then I said, and I want on the back cover, I want Don Quixote tilting at a windmill. With the same labels, okay, to say this isn't, basically sort of saying, it's propaganda that you need all this great stuff that we're going to teach you about, but really, it's just all nonsense. I don't know. Anyway, it turned out that in fact these tools were useful. So with the second edition, we dropped the back cover. Anyway, so Greener, he looked at he was pretty scared, but fortunately he had a good sense of humor, and he decided he would get AW artists to do that. And he says that when the book came out, the president of AW came into his office with that book, and he said, "Look, this is either the best cover we've ever done, or it's the worst, and I think it's the worst." And then he says, "Well, 3 months later, after he saw the sales, he came back and said, okay, it's the best." The interesting thing is, in fact, I'd insisted that the dragon tail appear on the the edge of the book. I forget what it's called, spine. Yes. And kids apparently enjoyed carrying it around, and because it was such a cool cover, so they'd take the course. Okay, and that was apparently an effect. And so I don't know whether the cover actually had any influence in drawing people into computer science, but it may have, at least in a few cases.
So it was a bestseller immediately, like
pretty much, yeah. I don't know what you call it, a bestseller among texts for advanced courses.
Yeah. So talk about the impact and the legacy of the Dragon Book.
Well, let's see. I'm not. I mean, there's no question that there was a time when, first of all, every computer scientist had to take a course in compiling. That's no longer true. And they pretty much all used the Dragon Book. What its legacy is, I don't. It's hard to say what influence it has today, or who got their start reading the book and then went on to do something, maybe having nothing to do at all with compilers, but did something important. I don't know. I would say this, that its usefulness as a text has gone away, and I think that's probably true of most textbooks. Certainly, most of all of my textbooks. When I'm occasionally asked, I tell people it doesn't make sense to write a textbook anymore. If you have something, first of all, there's no real money in it, because you go, there are these file sharing services. Anybody who wants the book, can just download it for free. I think people tend not to use required textbooks in classes anymore. Wikipedia really pretty much serves as anybody's textbook on any subject you need. So I tell people, if you know something that's worth telling, write it up, put it on the web. It'll get used, but the need to publish in a book form is just really not there anymore, and you can sort of see it. Basically, publishers of textbooks are kind of in a death spiral. They sell fewer and fewer copies. I think the Dragon book sells like a couple hundred copies a year, which is, in its heyday, it sold like 20,000 copies in a year. If you're not going to make any money, why do you, just put it out there anyway, and if it's good, people will use it. For example, the last book that I wrote, and I mean that in two senses, both most recent and the last that I will undoubtedly ever write, the data mining book with Leskovich and Roger Raman. We published it through Cambridge University Press, but they gave us permission to put a free copy on the web, which we do, most, ironically, because it's free, a lot of faculty, don't feel embarrassed about requiring that people read it, and some people will buy the text. And so the book sells more hard copies, I think, than the books that aren't free. It's it's a tricky issue. I'm not. I feel bad for the publishers who, by the way, used to perform a very important function. Essentially, they were the gatekeepers. They were the ones who had to figure out what intellectual materials were worth publishing. And that required them. First of all, it was an expensive proposition. They needed to have editors who would manage, reviewers. They need professional reviewers. That it's not an easy thing to figure out. Nowadays, just everybody puts everything out, and Google decides which are most popular. And if you need materials to answer a certain question, Google basically will show you the things that are most likely to be useful to you. So essentially that whole vetting process and deciding among what's worth publishing and what's not, that's just been automated, and it's much more efficient, much more democratic also. I don't know. I guess I'm off on a rant again. So
no, I think it's fascinating because you have written many textbooks and at least up until the internet, textbooks still were extremely important for the field.
Oh, right. Sure.
And so it's interesting to hear your thoughts on textbooks and the writing of them and the importance or the impact of them. So you mentioned earlier you had gone back to Princeton. What year was that?
I mean, to teach.
Yeah.
Yeah, I guess I started in '69.
Okay.
Wait.
And you decided to go back.
Yeah, that's right. 69.
For what reason?
Well, I actually, I guess I'd always had it in my not always, but at some point I decided I really wanted to teach. And the again, it's interesting. In those days, being an assistant professor was a crappy job. Today, at least a good university puts a lot of money behind their assistant professors and helps them to develop, to become something important. In those days, assistant professors were just there to, because the full professors didn't want to do a lot of the nasty little jobs that, so you had, an attitude like Harvard, I think, was a good example, where basically assistant professors were almost never given tenure. That you had to compete for your job. I think that stopped, at least in computer science at Harvard now. It's a pretty normal, that they have a pretty normal approach, which is we try to, we try to nurture you and help you to be worthy of tenure. That was simply not the case at the major schools. So I don't want to go through this, and so here I have this nice cushy job at Bell Labs. I have all of the privileges of academia. I even actually taught a night class at Columbia. And none of the responsibilities. I have, all the research, the resources I need, and complete freedom to do what I want when I want. So I went. And again, it's interesting how accelerated things. I think I spent accelerated things are compared to what they are now. I think I spent like 3.5 years at Bell Labs, and I was able to get an associate professorship. And again, I was still
at Princeton.
At Princeton.
Okay.
Yeah.
So you were able to use your position at Bell Labs to jump straight to a tenured job at Princeton.
Well, it was actually technically not tenured, although it was. It was. The way they explained this to me was that it was sort of a reserved tenured slot. That is, they wouldn't give me tenure for 2 years, but I didn't have to compete for it. It was set as. By the way, I think Princeton not only authorizes departments to have tenure track positions, but also tenured positions. So sometimes an assistant professor at Princeton could be up for tenure, but there's no tenured position. There's no slot open, so they can't have it. So it was put aside for me, and eventually I did assume that. But again, I didn't even think about moving pretty much out of the New York area. I guess Yale was starting a computer science department, and I was given an offer there, which I'm very glad I did not take, because it turned out. They hired this guy, Pete Wiener, who had been on the faculty at Princeton. In Princeton, they didn't give him tenure. at Yale, but they made him chair of the department. Yeah. Well, you can do that. There's nothing, there's nothing impossible. It's not a contradiction in terms. Well, he was the one who was supposed to build up computing, and he did a reasonable job. Hired some decent people. And then they said, well, you haven't been doing any research, so we can't give you tenure. Goodbye. So anyway, I went back to Princeton with the goal of building up computer science. I should say, the computer science guy, which was Ed McCluskey, had gone out to Stanford. Anyway,
So you replaced him, basically.
Yeah, I was. I was supposed to be the guy who would build up computer science, and I don't know. You probably want to get into my experiences during that 10-year period.
Yeah, sure. One other thing is that you mentioned you never wanted to move out of New York. So were you commuting to Bell Labs and to Princeton from New York?
Oh no. We lived in East Orange. It was a little commute. When I was at Bell Labs, then when I took the job at Princeton, we had faculty housing down at Princeton.
Okay. So then, go on to talk about, once you got tenure.
Well, that's as I said, after 2 years, eventually I did get a tenured position, and then eventually got promoted to full professor. But I guess it was really, pretty productive time of my career. I had a lot of good graduate students, and we did things. A lot of the code optimization work came out. Then, interestingly, I needed to. Basically, we had an open position that we couldn't fill, so I hired on a 1-year basis Catriel Be'eri, who had just finished a postdoc at University of Toronto. Where he was working with Dennis Tsikritsis, who, by the way, was a Princeton alum, teaching there, and he had a student, Phil Bernstein, and Bernstein was, I guess, the first one to notice that there was a budding discipline database system. That is, people were beginning to think about specialized systems to deal with large-scale data. And Ted Codd had published his paper in 1970 on the relational model, and there was a lot of really muddled theory going on. And Phil Bernstein was the first one to sort of say, hey, you guys have two different, definitions of the same thing, and they're different. They're not equivalent, and which do you mean? And so Barry picked up on this field, and then when we hired him at Princeton, he taught a course on relational database theory. And so I and a number of my students, listened to that, and for I guess the last half of my time at Princeton, we were trying to develop a theory of relational databases, really, and that was a lot of fun and productive. Although I ultimately decided I had to leave Princeton because the politics were just too ugly, and I didn't know how to deal with them. I really regret not having learned earlier how to deal with academic politics. Because what was happening, again, you had me, who was I'm an associate professor, or the junior guy, and then there were these three groups: the solid state, the communications, and the computer. Now what we now called computer science, and the senior faculty were not computer scientists, and the young faculty were. And the students, about 2/3 of the students were specializing that were in EE, were specializing in the computer science track. This is undergraduate program we're talking about. So the old guys determined where the money went, and so you had their students, their graduate students, TAing in computer science courses, right? Because they kept the money for themselves, gave us the work, and now. So I guess it was in 78, I decided I had to leave, and I actually got a meeting with the president, Bill Bowen. And what I should have done was explain the important scientific problems that computer science was trying to solve. And, how computer science was affecting industry and so on, and the applications. And that's an academic argument for saying, put more money into computer science. Instead, basically what I said was, they're being mean to me. And, so what could Bowen say? Well, really, I'm sorry that you're unhappy. I'll try to tell them not to be mean to you, but he wasn't going to do anything to make the money flow in the right directions, where we could, let's say, support computer science graduate students TAing computer science courses. That was, and I just did not know, the right academic arguments to make. And so I left.
And so how did you decide to come to Stanford?
Well, at that time, now still pretty much, Stanford was the number one place for computer science. Don, at that time, I actually had an offer from Harvard as well, a couple of other offers, and Don Knuth said to me, look, you can make the same decision, you have to make the same decision that he had to make. He said he could either have gone to Harvard and convinced the senior faculty that computer science was important, or you can come to Stanford and do computer science. Because we've already basically made that argument. And so at that point, my wife was not at all happy to be leaving her family in the East Coast. But we came out, and it's it took us especially my wife, a long time to adjust to being here. But now she wouldn't leave. And it's funny. I'm thinking. Remember, I mentioned that my cousin was married to Herman Chernoff. So Herman was at Stanford. I guess at the time when I was working for Ginsburg in '65, I came up and I visited them here, and I asked my cousin Judy, how do you like living in Stanford? And they'd been there 20 years, I guess. And she said, yeah, I still miss Buffalo. It's hard for me to adjust. Buffalo is where they were from. It's hard for me to adjust. And 30 years later, after they'd been here 30 years, I asked her the same question. And she said, oh, we really love it here. And then, of course, they moved back east. But it was sort of like the same thing with my wife. It took her like 30 years to say, I really like living here. But, and there's no question, it was a wrench, moving out, and being away from basically really anybody that we were familiar with. But I'm surely glad I did it because, again, as Don Knuth said, I didn't have to fight for computer science. I just did computer science.
So you continued your database work at Stanford?
Yes, it was. I did database stuff, and then VLSI algorithms was a very hot thing. I got into that a little bit too.
Right. So you first. Let's talk about the database. So you established a lab for database research at Stanford.
No.
Oh no. Yeah.
Well, I mean, I did database again. It's funny. Yeah, I guess today every professor has a lab. I just had students.
Okay.
And, at first it was Gio Wiederhold was also in the database. So he was the database guy when I arrived, but his viewpoint was very much different from mine. Again, I'm a theoretical guy. Gio was not. But we did. I mean, together we started teaching some courses, and at that time, the subject was not even sort of recognized as an academic subject. So Stanford was really one of the first places to be offering database courses. And then, but it took a while. I mean, again, a funny story. The year before I left Princeton, we hired one of Gio's students at Princeton, Hector Garcia Molina. And he did some very interesting work for 10 years at Princeton. And then finally got the go-ahead to build up the group. So we brought him, we rehired, I'm sorry, we didn't rehired. Well, I hired Hector for the second time, but this time at Stanford. And, and he really was mainstream, a database guy. We hired, a couple of years later, I think we hired Jennifer Widom. And then the four of us, modestly, by some measures, we were the top database group in the world. So it was, but we still, well, I guess by that time we called ourselves a lab, But what it really was a Friday lunch we had. By the way, a great thing. If I have to give Hector credit for doing this. Basically, you get people from my students and Gio's students and his and Jennifer's. You get them all together for lunch, and we take turns talking about our research, especially the students, and you get the shared culture, And again, I had theoretical students; they had students who were doing systems work, and we talked to each other, and I felt that was just so valuable. To let people see how other people are thinking, what other people are working on, where there's not 100% shared vocabulary, but it's maybe 75%. So you can kind of understand what people are doing, and it's worth making the effort. Again, another key part of the the database lunch, as we called it, was people had to give trip reports. If you went anywhere, you had to give a trip report. It could be I went to Costco and found a sale on this, or I went to a conference or vacation. What it did was it made people sort of invested in each other's lives. You got to know personal items about your fellow students and faculty, and again, that I just think it was a just a very valuable experience for students, and it's too bad. When Hector passed away, it just sort of all fell apart. And Jennifer, of course, is now dean of engineering, so she's not involved in it. I'm retired. Gio passed away. Not going to happen again. But anyway, that was our lab, I guess.
Yeah. Let's talk about how you got into VLSI.
Let's see. I'm not. I know. Well, let's see. There was a big effort at that. Shortly after I arrived at Stanford, I guess the early '80s, there was this what's called the Meade-Conway approach, and the theory was anybody could design a VLSI circuit. If you could learn to program, you could learn to design a VLSI circuit. And they had what I guess is a very simplified view of of what a VLSI circuit looks like, and so it looked like this was going to become something that computer scientists should be interested in, and at that, and also I guess Jim Gibbons, who was the dean of engineering, was building up the first of these centers. Stanford, as you probably know, and many other universities now, also will have these industry-related centers where companies pay, donate money to become part of a research operation. So Jim Gibbons and Jim Meindl were putting together what's called the Center for Integrated Systems. Still exists. Was, I guess, later endowed by Paul Allen, in fact. And it was supposed to be a joint CS EE operation. It turned out to be pretty much more EE because it had its own fab. So, all the money really went for the fabrication, but the idea was that there were interesting questions for computer scientists to answer about basically designing algorithms, and it was a new form of program. Think of it as a new form of programming, I guess. So it intrigued me. I guess I had a couple of students who did. Okay. In fact, now I remember. In fact, I had a couple of students who did theses, and in fact, there were. Now I remember there were two students at Stanford who, on their own, had developed a chip using this Meade-Conway methodology. They called it the guitar chip because it could simulate the strings of a guitar. And there was nobody in the department who was willing to advise them. So one of the things, I always felt that it was my duty to help students if I could. So basically I took them on. And that's what forced me to learn a little bit about, the Meade-Conway world, and I got, I was at one point I was even supposed to move my office over to the CIS building, but I never actually. I just didn't feel comfortable doing that. It was all of my other work was with the computer science people, but I even wrote a book on VLSI algorithms. Didn't sell much. As I guess Ron Rivest, it was the R in RSA. Also, I guess it got the bug at that time, and I remember him saying, "There's a lot less to VLSI than meets the eye." So after a while, I just sort of dropped it.
So I read that you also wrote a book on ML. Is that the programming language?
That's correct. Yeah, why did I do that? For a while I was teaching the sophomore course, and I forget why, but the person who had been teaching it previously had them learn ML, which it's a very interesting language, and probably was worth teaching just because the paradigm is so different from C or C++ or Fortran, that kind of thing. I do that. I had to learn the language myself, and at that time, it's, okay, I'm gonna have to put together some notes, so the students can learn it. So I might as well make it into a book, which I did. And again, it didn't sell all that much, but I think it got a decent share of the ML market, which was never all that big. So.
But you're teaching a course. I guess you figured you might as well make a textbook out of the teaching material.
That's absolutely right.
Yeah. So, speaking of textbooks, so then in '92 you published Foundations of Computer Science with Aho.
Right. Yeah.
So how did that come about?
Well, again, we, for reasons I forget, decided that that we needed to get, we wanted to just change the way, computer science is introduced. That it's, our view was, and I think still is, I think I can speak for Al, is that the theory and practice are two sides of the same coin. So we wanted to write a book from that perspective, where you give the theory and the programming applications at the same time, and so that was what that book was really all about. For example, I think a key example is, if you're a mathematician, you think about inductive proofs. If you're a computer scientist, you think about recursive programming, but they're really the same thing. Okay, it's you get a big thing, by using a little thing, or the thing below it. Anyway, again, that was another book that never really sold very much. Although we were able, that was the first book we were able to get the copyright back, and we just put it out on the web. And I think it's still used to an extent. It's it's kind of out of date. It uses the C programming language, not even C++. It's just, but I still think there are, the ideas, the basic ideas are all there.
Yeah, I mean, at the time, compared to other maybe introductory or foundational computer science books, what, was it impactful? I really, it's hard to say. Again, remember, it's not an introductory book. It wasn't designed to teach people how to program. It was designed to teach people who already knew the rudiments of programming, how to do inventive stuff with, using, the most useful data structures and the basic algorithms that everybody, we felt, should know. I think, again, the fact that it's still used, says, well, yeah, we kind of, got it right. Obviously,
there are many more modern approaches to the same subjects, but I like to think that it had some good influence on the field.
So this would have been appropriate for a second or a third year undergraduate, or?
We thought of it sort of as the second course,
Okay.
probably sophomore level.
Right. Okay. Right. Okay. And for this book, you chose turtles for the cover.
Oh, yeah. It was sort of the idea that we had supporting the symbol, the things on the turtle's back represented, let's say, the upper class courses, the books that were used in upper class courses, that the turtle was supporting all of these. At least that was our idea, and I think that makes sense. You needed to have these basic algorithms, data structures, and so on before you could start doing operating systems or compilers.
So how do you come up with these interesting textbook covers?
I don't know. There haven't been that many instances of it,
Is there a through line, or is each one?
No, it's just sort of random.
Okay.
Some work, some don't.
Right. So you served as chair of the computer science department at Stanford from 2000 to 2004?
Something like that, yeah.
Okay. And you retired from Stanford at the end of that period?
No. I think the last day of 2002 was my last day as active faculty. But it might have looked like I retired after that because I never really did anything very important afterwards. It pretty much finished me my career. At least my research program never really got started again.
Mm-hmm. Right. Too busy with departmental.
Well, when it was serious business, being department chair, and so I don't know. My research sort of fell off and never really restarted. It is unfortunately a young person's game, computer science research.
So when did you start working with industry startups?
Well, I didn't know that I had. I mean, a couple of some of my students started things, and some quite successful. So I was involved in peripheral ways, but it wasn't. It wasn't a thing that I said, hey, I got to get involved in startups.
Right. So it was mostly through your students that.
Yeah. I actually did start a company which still exists, but we just sort of run it as a hobby. The idea was to automate homeworks in a way that could actually teach students how to solve the problems, and at the same time test that they had that they had solved it. It's called Gradients, and for a while we thought we could make some money doing it. Turns out you can't. So we just sort of run it as a hobby. Gets about 10,000 students a year taking it, using our materials, but we haven't really kept up with, it's the same questions from, 10 years ago that people use. They typically, faculty who use it create homeworks using the problems that we offer them, although they can make their own if they want, but they don't. That's anyway, it was an interesting experience, but I occasionally serve as an unofficial advisor to startups here and there.
And Sergey Brin was one of your students?
That's correct.
Could you talk about working with him?
Yeah, well, again, the key thing is with a student is to just get out of their way and get them the resources if they need them. In Sergey's case, what he needed was disk. So I wound up, basically my role is to buy him some disk so he could put a copy of the web on. Let's say Sergey obviously was an extreme point in someone who didn't want to be advised. He just wanted, someone to make his life simpler. And there are many. I've had many students who are like that, who basically told me what they wanted to do, and I had to sort of carry along, or let them carry me along. And then there were others who really needed, to be coached gently into the process of doing, doing serious research.
Are there any other graduate students that you'd like to mention?
Well, I'd almost like to mention them all, but let me just say I'm really proud of what my students have achieved. I mean, many of them are either have become major research figures or major commercial in the the tech field. You can there's a list of them. I have a list of them online. It's
So have you been on, or are you still on any boards?
What? Well, of boards of directors.
Yeah.
No. Then that's not. I haven't done that very much. I tend to be more on advisory boards. I think I'm finishing up a stint on the Tata Consulting Services. I've been on their advisory board for many years. Just finishing that up. Again, I'm informal advisor to a couple of startups. What else? I'm getting old. I'm really not. not able to do all that much. I've been refereeing proposals and things like that for various organizations. But I try to avoid positions of authority, and the world seems to be pretty happy with that.
Can you maybe reflect on the differences between the research lab environments of the 70s, like Bell Labs, and the startup-driven world of technology today in Silicon Valley?
Well, I mean, there's really no comparison. As I said, Bell Labs is a unique situation in that there was a mandate for them to spend money on research. And, all right, but there are a few industrial research labs that, are similar in nature. Like, Microsoft puts a lot of money into research. I think, let's see, who else? Yeah, the big tech companies tend to have at least some pure, well, I said pure but applied research going on. But a startup is just very different. They may be doing research in the sense that nobody knows how to do what they're trying to do, and then they have to figure it out, and the successful ones do. But essentially it's exactly the opposite. The two opposite approaches. In industrial research lab, like a Bell Labs type thing, it's broad spectrum. We're hiring you people, just go in whatever direction you want, and the ones that work, that's great. If you're a startup, you have very limited resources. You have to pick a target and devote all your resources to that target and that target only. You can't let yourself be diverted. You can't afford to have somebody who's really bright but not 100% aligned with what you're doing. And there's no harm in that. For one thing, at least in computer science, startups tend to be startups for only a few years. Right? So there's nothing wrong with spending 3 years with a single-minded goal. Even if you wouldn't want to spend your whole career on it, because either you'll be successful and then there'll be something, there'll be the resources for you to move on to something, either push it or as happens in a number of interesting cases, like look at Amazon, look at the businesses that they started off selling books, and look at what they're, now they're a cloud service. You can stay with a company that's successful and go off in all sorts of different directions. It's probably not that different from what you might do if you were at a research lab. Well, I guess we kind of That to me, that's the distinction, and they're both good, and people often jump from one to the other.
I mean, there's some people feel like there just isn't the heyday of industrial research labs is gone. That most of the work being done has been directly applied in industry now. You don't have you don't have as much stuff coming out of research labs, like your Bell Labs or your Xerox PARCs anymore.
I'd have to say I beg to differ. Well, for example, I don't know whether you consider, let's say, OpenAI to be industrial research or not. But but also you do have comparable things coming out of industrial. They're in fact, I think all the mega caps, as they call them now, or Magnificent Seven, they're all all doing research on things like LLMs and driverless cars and many. I gather a lot of hardware architecture is coming out of these companies, and it's all research. It's all research. It's all research. All real research.
But maybe it's not as much blue sky or pure.
The weird thing might come out of academia, but it's hard not to categorize, something like, develop driverless cars. It's a good example, right? The first one was really it really came out of academia, driven by DARPA, really. But there's still so much that's not known about. They certain, they're not perfected. The basic idea may be understood now, but they're not perfected, and they're not perfect, and there's still hard problems to be solved. I think the same is probably true in a lot of the LLMs and other AI related things. The biggest systems may have to come out of industry because they have the resources, but there are certainly ideas that I see coming out of academia. For example, I've seen a number of academic papers on how to focus these LLMs. Elimination of the hallucination problem. That's the kind of thing that doesn't take mammoth, the mammoth platform that you need to actually do the training. Ideas count more than the hardware resources. So no. I think that there's still, as there has been in the past, plenty of room for good work, both academic and industrial.
Okay. And you've continued to teach even after your retirement. Is that correct?
Well, a little bit, not doing it now.
Right. And one of the courses that you taught was on bridging policy and technology.
Yeah. That's interesting. That was not my idea. It was a Stanford undergraduate who basically convinced me that she wanted to do this. And so she basically ran the thing. And I got mentors, got some of my friends. Constanza Hasselman is her name, by the way. Very brilliant kid, really, and just able to, she really organizes things herself, and I just got sort of dragged along. Then she graduated, and the whole thing fell apart.
So. And of course, your recent work, you've continued to work in databases and more recently data mining, right? Is your more recent book that you mentioned?
That was sort of the last, last area that I kind of worked in.
Right. What year was that book published?
Oh, good question. There's been a couple of editions. So I think the first edition may have been 2007.
Okay. I mean, has obviously with the rise of machine learning, has this field gotten more and more important?
Well, I think that machine learning sort of demonstrates, how important access to massive amounts of data is. I mean, you couldn't, look, I spent most of my career sort of sneering at artificial intelligence because I felt that they were asking the wrong question. They were trying to simulate human thought. And, that it did some interesting things, but it really didn't get anywhere. And it wasn't until you had access to these just massive data sets like the web, which, and it became possible to develop new kinds of algorithms that took advantage of the existence of all that data, and so it was at that point that machine learning, which again, remember, is something that goes back, I don't know, at least to the 80s, where it was just considered, it was, programs that improved themselves based on experience. Interesting idea, but it doesn't really get you anywhere. It's only when you realize you can turn data into an algorithm that that something really was achieved, and now it's just amazing what you're able to achieve and all of the various ways in which you can turn data into algorithm.
And so this work also dealt with parallel programming in the cloud?
The data mining, we covered, Again, that does seem to be, first of all, now everything has to be parallel, right? Moore's law, in one sense, died 20 years ago, in that chips are getting a little better, but not much, and all of the reason that we're still able, it looks like Moore's law is still working for us, is you're able to assemble more and more of this, more and more processors together and make them work in concert. So everything, all big data algorithms depend upon parallelism in one sense or another. And so we, I guess I was personally interested in MapReduce algorithms. That was a topic that I spent a couple of years thinking about. So I wrote a chapter for the book on that sort of algorithm. But it looks it looks like it's still tools like the Databricks Spark system is an example of something that gives you the parallelism in an easy way. But the parallelism has to be there. And if you want to do any of these things, you have to know how, any of the really interesting big data algorithms, you have to know how to get parallelism working for you.
How did you get interested in this area?
Which
big data?
Well, I think it's a natural outgrowth. I mean, this is what database systems really is. It's how do you manage the largest data sets that are available at that time, right? And that's the history of database systems. Right? It started out, it was, General Motors payroll, managing the General Motors payroll. Now it's learning how the web talks about subjects, so you can parrot what the web would say about any given topic. That's what an LLM really is. So it became natural to, if you're a database person, you had to start thinking about ways other than relational databases to handle really large data sets. So essentially, every database person these days has become a big data person.
Right. So it's the natural extension of the database, the natural outgrowth of that. You were elected to the National Academy of Sciences.
Yeah. Go figure.
Yeah. What year was that?
2020, I think I was in class. Because with COVID, it wasn't too clear.
Okay. And is there anything you want to mention about that?
Well, not sure what can be said. Although an odd story, I guess when I was inducted, I filled out a questionnaire about interests. So, what would I like to do? And I thought I was volunteering to referee some papers for the proceedings of the National Academy of Sciences that they have. Turns out, I had actually volunteered to become an editor of the journal. Now, as you know, I assume computer scientists don't publish in journals. So here I am. I'm actually one of two of the 300 members of their editorial board. I'm one of two computer scientists. And I've been trying to get other people involved, especially people in AI, because a lot of the papers, of course, that come in are, a new machine learning algorithm for doing something that is of interest to some scientists in one of the many sciences, of course, that they cover. I know nothing about this. So it's one of the things that's kept me kind of active, more active than I really want to be at my age.
So this is a question that I asked Al, but with the rise of machine learning, the word algorithm has gotten a little bit of a negative connotation. What's your sort of response to that?
Yeah. I mean, I get it that it's used. It's a particular kind of algorithm that's used to, decide things that you'd maybe rather would decide for yourself, or things that affect you in ways you can't understand. I hadn't thought about this, but I guess it is unfortunate that the term is now being used to refer to a particular impact that particular algorithms have, and that most algorithms have nothing at all to do with. I'm not sure what you would what we can do about that. I think the concern is legitimate. For example, if your insurance company uses an algorithm to predict your probability of having an automobile accident, and it raises your rates as a result, that's an algorithm, yeah, and it has a negative effect on you. But the problem is not that it's an algorithm, obviously, but that people are using it in a way that is both unexplainable and possibly arbitrary. What can I say?
So what is the specific class or subclass of algorithms that you're referring to?
Well, what I assume, again, what I assume when we talk about a negative connotation of algorithm, I assume it's an algorithm that is making a decision. First of all, it's making a decision that affects you, and you don't have access to what it's actually doing or why.
So it's not that there's like a theoretical type of algorithm that it's not that. That's the problem.
I don't think so. I mean, look. People, even without computers getting involved, right? Let's say an insurance company, they would, draw a line and say people living in this area, or certain that line, a circle, people living in this area have a higher probability of having an accident. And not a computer algorithm. It is, some person has made a decision, and it affects the people inside that circle. So companies and governments and schools and everything, have been making decisions that affect you, and you don't, and you don't need a computer to do damage, or to do harm. So I, you're not, if you're talking about a remedy, I don't think you could say, you can't use a convolutional neural network because they produce bad algorithms or something like that. That's nonsense. There are algorithms, that are from the algorithm's point of view, are very different, but can have negative effects, and there are algorithms that have very good effects. And then there's some that are ambiguous ones. Like I find it, for example, very convenient that Google and Amazon and so on, they kind of know what things I might want to buy and recommend things to me. I don't have to buy them. There are other people who freak out about this, who, they worry about the fact that somebody knows that, that they're a vegetarian or something like that. But it's not the algorithm's fault. It's a tough policy question. I'd have to say I've never been a big fan of privacy. I always remember one of the things that I learned from Gio Wiederhold. He said that privacy is actually a very modern construct. 200 years ago, you lived in a one-room house. Everybody knew your business. You were in a small village. Everybody knew your business. Nobody had any secrets from anybody. And then it wasn't until the rise of large cities that people could live anonymously. And now, thanks to the internet, we're all part of a global village, and everybody knows everything about everybody else again. So get over it. And that was his point of view, and I think it's pretty much my point of view. Is that that you can't assume, a particular right to privacy. Now, if you want that privacy, you can do certain things. You can stay off the grid if you want. I don't think it makes sense to do that, but it's okay. I'm okay with other people wanting to do that, but again, in terms of blaming the algorithm, again, people don't need computers to do the sort of thing that these bad algorithms do. I guess it just makes it more efficient to do them, and they get done on a larger scale. But the good things are also getting done on a larger scale.
But in terms of privacy, though, don't you think aren't there certain things that should be private, like medical records, or maybe you don't want people finding out your address and coming to your house necessarily, or
Well, I don't want people coming to my house if they're not welcome. But medical records. Yeah, no, I am. I mean, there's a value to privacy, but there's also a value to Google finding out that I have some disease for which a medication has just become available and telling me about it. Right? I'm not. Yeah, I am. I'm not a big fan of HIPAA. Let's put it that way. I think. Again, if it's your decision, it should be your decision to make. If you want your medical records confidential, fine. But I don't personally.
Okay. Talk about receiving the Turing Award.
Yeah. I don't know.
Or let me rephrase. What has winning the Turing Award meant to you?
Well, I don't know. I have to admit, I never thought that what I was doing was Turing quality, and it's good stuff. Near that level. I was very surprised to find that I won the award.
I think Al also mentioned had a similar sentiment.
I don't know. It's I don't know. It's obviously it's feels good to be able to call myself a Turing laureate, I guess. I've gone a couple of times to the Heidelberg Forum, and that's a nice privilege. But I haven't really noticed that anybody, is more impressed by what I say because of it, and they shouldn't be. It's but it was cool.
Yeah. Maybe can you reflect on the development of computer science over your career and your impact on it?
Okay. Well, I mean, the high level, view is that it is during the time. Look, I'm not one of the founders of the field. I sort of like 10 years too late, born 10 years too late. But the field has grown tremendously in importance. The interesting thing is, basically from my late 20s, I've been a senior person in the field. This is something that doesn't happen very often in different fields. But basically it started off with a small people, who were really just starting out on their careers, that created the field. I don't have offhand the exact numbers or lines of code that have been written, or numbers of practitioners even, but the growth has, I think there are probably very few examples of fields that have grown such a pace for so many years. I don't know. My personal impact, I think it's through the books. It's not through research. The way, again, most Turing awardees have built some system that people use, or at least used for many years. I think that my contribution has been more in organizing, codifying, and disseminating, and making available, simplifying, in many cases simplifying to the point that it became accessible to a sufficiently large population. So if there's anything I deserve to be remembered for, I think it's that. It's not YACC exactly.
Okay. Would you like to add anything that I missed?
Boy, I think you've covered a lot. I'm trying to think. Did I? This is not my first rodeo, and I have, as you can probably notice, a couple of things I came in wanting to say. And now I'm trying to say, did I miss anything other than that? I'm going to guess not. I think we got the story. I think I gave a shout out to people I wanted to give a shout out to.
Where do you think the field is going, and what do you see in the future for computer science?
Well, I think in the really long term, I think it's going to sort of blend in with general knowledge. There's something that that every person grows up knowing something about, just as, well, let's say reading and writing was 500 years ago, that was a specialty, right? It was a field. It's what I suspect is that, and certainly in many countries, and I'm sort of ashamed that it's not true in the United States. You take basically software engineering as a high school subject. It's amazing. California, they're willing to mandate ethnic studies, but they're not willing to mandate that everybody should know how to program when they get out of high school. I think eventually that will happen. That it will become part of everybody's curriculum. Become less mysterious. Just as reading and writing and arithmetic are now, they were once fields. Now they're just stuff everybody knows. Just as pretty much any occupation involves, reading and writing, every occupation will involve some form of making, making hardware work for you, whether it's, just learning how to issue the right prompts or the right Google queries, or not. It'll just be part of it. It'll just be part of everybody's life. So I don't. If you look at recent trends, let's say to enrollments in computer science, I think it's beginning to sort of top off, but it's not going to go up exponentially until every college student is majoring in computer science. That's just not going to happen. But more and more people will major in whatever they major in, will know some. They'll know computing in some. To some extent, just as whatever your major, you have to know how to write a coherent paragraph, or get ChatGPT to do it for you. That's it. I would also. I'm surprised we haven't really talked about the doomsday cult that has grown up, about human beings are going to be replaced by their, by their own laptops, basically. I am, and boy, this is going to go into the archives, so I hope I'm right. That I don't believe that. That computing of any sort, whether it's AI or anything else that might come down the pike, I don't think that it's a what's the term, existential threat to humanity. We will probably have to be a little bit careful, especially with things. Once you start combining computers with actuators, sort of robotics is far more dangerous than machine learning. Let's say it's only when you get a driverless car that might decide on its own to drive up on the sidewalk and see how many people it can mow down before it's stopped. That is something you have to guard against. Algorithms that estimate probabilities of automobile accidents, they can't. They could be wrong. You might not like it, but they can't really harm you until you attach it to something physical that can do harm. And even there, I think it's far less likely that the software will decide on its own to do something it shouldn't do, than that somebody will, either the software designer will put basically a bomb into the software, or a hacker will break into the software to get it to do damage, which they do now anyway, right? Different kind of damage, maybe. I guess you got to count me as I'm an optimist, not a pessimist.
Yeah. What about social media algorithms that are radicalizing people or misinformation? Getting people to believe in misinformation.
Yes.
The political impact of these things.
I wish we could get that under control. I think it is a danger. But I think, again, I could be wrong, but I do think that people are beginning to understand that. Just as you have to learn when you get an email, that says the IRS demands this amount of money, send it in a gift card. You have to learn that that's not real. You're going to have to learn that a lot of the things that you read on in your social media are not real either. And I think people are learning that. Now there seems to be a class of people, which is unfortunately pretty large, that want to believe nonsense. Okay, and it is, but do you really think that it would be possible to stop these people from believing nonsense if they chose to do that? I wouldn't mind seeing some sensible regulation. Giving a social media companies a responsibility for at least identifying falsehoods, but it seems to me a practically impossible. I mean, just how do you first of all, how do you define falsehood? In fact, I used to think that medical matters were a different class. That is, you can in most issues, like whether the Earth goes around the sun or vice versa. It's not government's job to regulate a policy or determine truth versus falsehood. When it comes to medical matters, they are sufficiently important. You have to have the government able to say, no, don't swallow bleach to get rid of COVID. That there has to be you have to be able to rely on medical professionals to determine, let me say, the current belief as to what is true and what is not. Okay. Most things you can't do that. Okay. Or it's the disadvantages of trying to establish truth and falsehood are the disadvantages outweigh the advantages. In medical matters, I think the advantages outweigh the disadvantages of establishing truth. So how you legislate to tell, I think Facebook should have some responsibility for not letting nonsense go rampant, but it can't censor it either. So probably labeling is the right approach. But the trouble, look, by the way, I was reading an article that said apparently labels on things like cigarettes actually have a negative effect. That it promotes rather than by drawing attention to the product, it actually increases. And then there are some statistics that apparently, show that when things get labeled as dangerous, they actually wind up in usage increases rather than decreases, at least for a while. Okay. So I don't want to say, oh well, let's just require that Facebook label, put on any post that meets certain criteria, a statement saying, there's another point of view, please see this, or that. That's actually probably not going to help. So I don't really know, what might help, but also it's just, there are just too many different points of view. It's essentially an infinite set. So you can't do that 100% correctly. So some notion of best efforts might be useful. I wish I knew. I think it is a critical a critical position, but it's a critical issue. Is in how you manage disinformation. But I guess I do hope that at least the class of people who are willing, who don't want to believe nonsense, will learn how to tell when something is nonsense, or what the hidden motivation behind something is.
Okay, thank you. My last question is, what advice would you give to a young person starting out in the field today?
Sort of as wanting to do computer science.
Yeah.
Okay. Learn as much mathematics as you can. Probably try to learn a field of application. What else? You got to, take it seriously. You're going to work harder than your friends who are not doing computer science, but it's going to be worth it. Try to have fun, which will probably turn out to be impossible, but try anyway.